Welcome to the solutions to problem set number 15, where we take a closer look at cosets. Exercise 1. We take this subset of the integers mod 3. Clearly this is not a subgroup, because any subgroup would have to contain the neutral element, which is 0 bar, which is not contained in here, so this cannot be a subgroup. And we are supposed to check that in this case, when this here is not a subgroup, that then all the cosets do not form a partition of the whole group. Okay, this is easy. We simply take a look at the cosets. 0 bar plus this set here gives me 1 bar and 2 bar. 1 bar plus this subset gives me this subset, and then because 1 bar plus 2 bar equals 3 bar, which is 0 bar, I end up with this 0 bar here. And finally 2 bar plus this subset gives me 0 bar, 1 bar. And 1 bar here because 2 bar plus 2 bar is 4 bar, which is the same residue class as 1 bar. Okay, and clearly the union of all those gives me the whole group, but they are not pairwise disjoint, because for example here we have 2 bar as a common element, or here 0 bar as a common element, so no disjoint union, so these sets here do not form a partition of the whole group. So we see it's important that this here is a subgroup for the cosets to partition the whole group. Okay, exercise number 2. We are supposed to find the index of this subgroup here in the symmetric group of degree 3, or on 3 elements. And this here is the cyclic subgroup generated by this 3-cycle 1, 2, 3. Okay, this here I abbreviate with sigma, then H is the subgroup generated by sigma, and this consists of sigma itself, sigma squared, and sigma to the 3rd power gives me the identity, because the order of this cycle here is 3. So I end up with these 3 elements here. Now then, for all permutations in this group here, I get no new coset. So if I take the coset of pi, where pi is any element of this subgroup, with respect to H, I end up with H itself. We proved this, or we saw that this was a corollary to the lemma we proved in the lesson. So I need to take an element that is not in here, for example this transposition 1, 2. Then the coset, the left coset of this transposition with respect to H is tau composed with it, which is tau itself, tau composed with sigma, which gives me this transposition, and tau composed with sigma squared, which gives me this. You can check this for yourself or simply believe that this is true. And now clearly S3 is the disjoint union. Those are obviously disjoint, and the union of those two sets gives me all of S3. So S3 is the disjoint union, that's this dot here in the union symbol, of the left coset of the identity and the left coset of tau. So we have 2 different cosets. So the identity in tau is a complete system of representatives of these H cosets, and this is exactly the meaning of the index. So the index of H in S3 is 2, because there are only 2 different H cosets. Exercise number 3, we are supposed to find the index of this cyclic subgroup, where R is the rotation by 90 degrees, and this here is a subgroup of the dihedral group of the square, so the symmetries of all the symmetries of the square line here. And we saw many times that this here is generated by the rotation by 90 degrees counterclockwise and any reflection about one of the 4 symmetry axes. Okay, because this is of order 4, this cyclic subgroup consists of 4 different elements, namely those powers here, where R to the 4th power is the identity. So I have 4 elements in here. Now if I take any reflection, then the coset of this reflection with respect to h looks like this here. And obviously a reflection does not lie in here because those are all rotations and a reflection is no rotation. So the equivalence class of this here, which is nothing but the left coset, must be disjoint from this coset, which is the equivalence class of the identity. Or you simply argue that these here all are reflections and these are all rotations. So those two cosets are disjoint. And those here are 4 different elements. You could say, well, obviously, but it might happen that this here, for example, is equal to this here. But if this were the case, if I had this equality, then I could cancel the s by multiplying with s inverse or s itself. It's a self-inverse element. So it would follow that r to the I would be r to the j, which is not possible if I and j run between 0 and 3, because those here are always different rotations by different angles. And yeah, next week we're going to prove, which is actually pretty easy, that all the cosets have or are of the same cardinality, so we don't need this involved argument after we know that. And now I have a coset with 4 elements and another coset with 4 elements, which are disjoint, and since D4 only has 8 elements, it follows that D4 is the disjoint union of those two cosets. And again, the index of this subgroup in the whole group is 2, because there are only 2 different cosets. And when I was talking about equivalence classes or an equivalence relation, I meant exactly this one here that we are going to take a closer look at in exercise number 4. We have a subgroup, 2 arbitrary elements in this subgroup, and we need to show that the following statements are equivalent. The left cosets are the same, that y lies in the left coset of x with respect to h, or that x inverse y lies in h. Okay, this is pretty straightforward. So if these here are the same, I can simply write y as y times e, but e lies in h, of course, because h is a subgroup. So y times e lies in y times h, which is by assumption x times h. So y lies in the coset of x. Now let's suppose y lies here, and then we need to show that x inverse y lies in h. That's also straightforward, because if y lies here, by definition of this set, y can be written as xh with some element small h in capital H. And now simply multiplying with x inverse from the left yields x inverse y equals h, which is an element of h, and we are done. Now the last implication from here to here, because if we prove that from this follows this, and from this this, and from this this, we have shown equivalency. Because if I want to, for example, know that this here yields this, I simply go from here to here and from here to there. So instead of showing all the equivalences, I go 1 times round in a circle. So let's suppose this is true, and then we need to show that these cosets are the same. So if x inverse y lies in h, I can find an element h prime such that this here holds, and then multiplying by x from the left gives me this relation here. And then if I multiply y with any h from the right, so here, I end up with this. By associativity, I can move the parentheses, and now because h is a subgroup, this here always lies in h again. So yh is x times an element of h, and by definition it lies in xh, showing that y capital H is a subset of x capital H. And of course, the other direction is almost the same. You have to be a bit careful about the inverse here. So we assume that this here is true, or equivalently y is x times h prime, we can conclude that x is yh prime inverse, simply by multiplying from the right with the inverse of h prime. Now again, because h is a subgroup, h prime inverse also lies in h. And then if I multiply from the right with h, I end up with that. And by the same argument as above, this here is an element of the subgroup h. xh lies in yh for arbitrary h in capital H. So this shows the other inclusion. And together we conclude that both cosets are the same. The proof becomes much easier if we use our knowledge of equivalence relations. On problem set 6, you basically showed that this here is an equivalence relation. There the inverse was on the second group element, so this would correspond to the right cosets, but the proof is essentially the same. And if you know that, it's easy to see that this here is nothing but the equivalence class of this equivalence relation, and then we already know that this here is the same. If two elements are equivalent, they have the same equivalence class, and this is equivalent to the fact that one element lies in the equivalence class of the other. So simply by citing what we proved back then gives the whole proof. Okay, we are already at the final exercise of problem set number 15. We have a subgroup, then we know that we can partition the whole group into different disjoint cosets of the subgroup, and in this case we take the right cosets. Now I take an index set capital J, and the cardinality of this index set capital J is called the right index of H in G, and of course if this is finite it's simply the number of different right cosets. And it's not completely obvious that then this right index is the same as the left index we already introduced, where I partitioned the group into left cosets. We will be using what is given in the hint, namely that the inversion is a bijective, no, it's not given here, but we know that the inversion is a bijective map from G to G. So it's stated here. So G is the image of the inversion. This means surjectivity. So the inversion applied to all of G, which is exactly this set here. So if I take all the inverses of all the group elements, I end up with G again. And this here I abbreviate with G inverse, capital G inverse. And similarly, because H is a subgroup, also H inverse, which is exactly defined as this here, only with H element capital H, gives me H again. And now, if I take any left coset, GH inverse, so now if I take any left coset for an arbitrary element in G, GH inverse, this is by definition this set here. And now remember, GH inverse is H inverse G inverse. This is important if the group is non-abelian. And this here by definition is the right coset of G inverse with respect to H inverse, because I take all these inverses here, multiplied from the left. But now since H inverse is H, this is the right coset of G inverse with respect to H. And this here is the key. So this here will be the key for the rest of the proof. Now we already know that G can be partitioned into left cosets, where the index I runs through some index set capital I. It's one of the reasons why I did not call this map lowercase I, because we already have a lowercase I. But I called it inverse. Now we start with the observation that G is the same as G inverse, which is by the left coset partition, this here inverse. And now we will explain this in a minute. Bijective maps preserve disjoint unions. So this here is the same as the disjoint union of these images of the cosets under inversion. And as we just showed, this here is nothing but HJ GI inverse. which gives me that G can be written like that. And this is exactly a partition. Oh, this is crooked. This is a partition of G into right cosets. To finish the proof, we'll talk about this here in a minute, as I promised. This means exactly that this set here is a complete system of representative of right H cosets, because G can be partitioned in these right cosets where I runs through capital I. So I can choose as the index set J that I was looking for, simply the index set I that describes the left coset partition. So clearly they have the same cardinality, and this means exactly that right index equals left index. This is a non-obvious proof, I think. So for the final missing piece here, we use that inverse as a bijective map preserves disjoint unions. Let's prove this for two sets. This is enough. The idea for any number of sets is the same. So if F is bijective, then the claim is that F of this disjoint union of two sets A and B is the disjoint union of F of A with F of B. This is exactly what we have here, where our map F is inversion. So this here is inf of GIH. So first of all, this here is actually true for any map. So so if I map a union A union B under F, this always becomes the union of the images of A and B under F. But we need to show that this union remains disjoint. So if I have disjointness here, then here I also have disjointness. So let's assume there were an element in this intersection here of these sets. So we assume they are not disjoint. This means that Y can be written as F of some A, because it lies here, and as F of some B, because it lies here, with A and B and B. But now because F is injective, this already forces A to be equal to B. So A equal to B would lie in the intersection of A with B, because A lies in A, and if it's equal to B, it also lies in B. But by assumption, this here was a disjoint union. And this shows that the intersection of F of A and F of B again is disjoint, hence proving what we need here. Okay, that's it for problem set number 15. As always, I hope these solutions were helpful to you, and I hope to see you in next week's lesson. Bye bye.